In this video, we want to derive a relation between P and V in a process called adiabatic process. First of all, let me tell you, what do you mean by adiabatic process is? The process in which heat energy of the system is kept constant. We don't allow any heat energy either to get in or get out. So the total heat energy is constant. As heat energy is constant, change in heat energy equal to 0. We know, as per first law of thermodynamics, total heat energy supplied to a system is equal to sum of internal energy and external work done by it. That implies in adiabatic process, du plus dw equal to 0. Here, we can remember back our definition of specific heat of a gas at constant volume as amount of heat energy required to raise unit mole of a gas by 1 degree centigrade at constant volume. As volume is kept constant, change in the volume equal to 0. Again, as for the first law, dq equal to du plus dw, whereas dw equal to pdv. But here in this case, volume is kept constant, so dv equal to 0. So du plus p into 0. That implies dq equal to du itself. I can thus rewrite the definition of Cv as 1 by n into du by dt. That implies du can be written like n into Cv dt. If we consider for 1 mole of gas n equal to 1, that implies du equal to Cv dt. Once after knowing the value of du, I can substitute here in this equation du. I got the value of du. Let me also find out what is this dw. dw can be written like, as I told you, that implies from equation number 1, what we can write in the place of du, Cv dt, and dw means I can write pdv, where p is pressure, dv is the change in the volume. So as work can be written as pdv. That is equal to 0. Now I need to write this Cv dt also in terms of p's and v's. So I can remember back for 1 mole of ideal gas, as we already taken for 1 mole. Ideal gas equation is PV equal to nRT, but that n equal to 1. Now differentiating this using a UV formula, PdV plus VdP equal to R into dt. This implies I can write dt as PdV plus VdP by R. Thus, in the place of this dt, I can substitute this value of dt so that I will get a new format. What I will get? Cv in the place of dt, what we got? PdV plus VdP by R plus whatever is remaining. PdV equal to 0. So we are writing from this equation, right? From equation number 2 actually. Now let us multiply this with the R, the entire equation. Then Cv of PdV plus VdP plus P, that R will come to this side as you are multiplying with R. Here R got cancelled. Here R comes equal to 0. So I can elaborate this as Cv PdV plus Cv VdP plus PR dV. So what I can take common here is PdV, PdV. So from these two terms, if I have taken that PdV common in the first term, I will get Cv. The second term I will get R. So Cv plus R, PdV, plus what is remaining is Cv Vdp, that is equal to 0. But we know the relation Cp minus Cv equal to R implies Cp equal to Cv plus R. So in the place of this Cv plus R, I can write Cp, thus I will get a fresh equation. What is the fresh equation we will get? In the place of Cv plus R, Cp. What is remaining is PdV plus Cv Vdp equal to 0. I got an equation now, and I need to simplify that further. See, I got an equation, but I got an expression, I got a relation, but this is not the relation I want. I want it in some another format, P and V power format. I need it in terms of P and V. So what I will do to get this in terms of P and V is, I will divide this entire equation number 3, dividing equation number 3 with CV PV. You may get a doubt why we shall choose this CV PV. Why not some other term? You just once divide so that it will be unfolded and you will see what is the result that I am going to get. So divide this equation number 3 entire equation with CV PV with each term. So the first term is Cp PdV by, as it is given, Cv PV, dividing with this. Further, the second term is Cv Vdp and divide with Cv PV. On the other side also 0 by Cv PV. Now you see, this P and this P can be cancelled. This V and this V can be cancelled. This Cv and Cv can be cancelled. So what is remaining? Cp by Cv, and what is remaining? dV by V, plus what is remaining? dP by P. 0 by anything is equal to 0. That implies Cp by Cv is nothing but gamma as per the definition that we had earlier. So gamma dV by V plus dP by P equal to 0. So if you have now looked it again, because we have divided with CVPV, this entire equation is converted into a new format of P's, V's and gammas. That's what we need. So dividing with CVPV makes a perfect sense so that I can get into the format that I need. That's the reason why we are dividing only that particular term. Now let us see further. We got an equation and let us integrate that equation to get into the format that we need. Integrate the above equation. Integral of gamma dV by V plus integral of dP by P equal to integral of 0. Gamma is a constant and we have a formula. Integral of 1 by x dx is nothing but equal to log x. So integral of dV by B will be log V. Of course, base E is there. Plus integral of dP by P is log P base E. Integral of 0 is equal to a constant. Now as per the basic law of logarithms, I can write it as log V power gamma base E plus log P, of course base E, equal to constant. Now by simplifying it further, we can get log m plus log n can be written like log mn, so that becomes log PV power gamma base E equal to constant. So if you take anti-logarithm on both sides, PV power gamma is anti-logarithm of a constant is also a constant. So the result that I have got is PV power gamma is constant in a process called adiabatic process. So in adiabatic process, being the temperature is not constant, Boyle's law is not valid. PV is not constant, rather PV power gamma is constant, where gamma is ratio of specific heats. So you can write P1V1 power gamma is P2V2 power gamma. This gamma depends on the nature of the gas. We will talk about that gamma value in some other video. That's it. That's how we want to derive. We need to derive expression for the relation between P and V in a adiabatic process. Thank you for watching.